Another very short and easy to digest section in this chapter. It's called molecular effusion and diffusion. So let's look at an observation. What we have plotted here are the fraction of molecules within 10 meters per second of an indicated speed versus the molecular speed. And what can you notice? Well, you can see on this side we have oxygen. Oxygen weighs 32 grams per mole. It's diatomic. And you can see on this side we have hydrogen. And hydrogen weighs it weighs 2 grams per mole. So the observation you can make from this data is that the speed of the gas is directly related to molecular weight. And just for purposes of illustration, what we're going to do is we're going to calculate the root mean square speed of a molecule of oxygen at 20 C. Why are we doing this? Because once it appeared on a midterm exam. So let's see what we get. This is the symbol for root mean square speed, and we are going to take 3 times R. Now what we're going to use here is the other R, 8.314 kilogram meter squared per gram squared mole Kelvin, okay? And we're going to multiply by temperature, 293.15 Kelvin. We're going to divide that by 32 times 10 to the minus 3 kilogram per mole. Then we're going to take all of this and we're going to take the square root. That says our root mean square speed is 477 meters per second. But since we don't really think in meters per second, we're going to switch that to miles per hour. I'm just going to do it here. 477 meters per second. We know that 1 mile is 1609 meters. And we know there are 3,600 seconds in 1 hour. That tells us the speed of oxygen is 1,069 miles per hour. Well, think about an object moving at that speed, past Mach 1. But that is what oxygen is doing as it's rushing past you right now. Why are you not knocked over? Well, the main reason is oxygen is very light, all right? And that's why you are not knocked over. So again, the equation is, derivation is beyond the scope of this course, but calculating the number and thinking of oxygen molecules we're currently breathing, that is within the scope of this course. So what else do we have here? Well, we have to talk about diffusion versus effusion. Diffusion is a bulk process, and it's the spread of gas molecules through a space. If we were in the classroom, I would be passing around balloons with a liquid inside. And you would smell that balloon and you would say, that smells like vanilla. Well, that would be my demo to show you diffusion, okay? The other term is effusion, and that's the picture right here. It shows the escape of gas through a hole in evacuated space. So there's like a little hole here, and there's a gas molecule going through. So I've questioned over the years why we're doing this, but again, I'm following the textbook, all right? So when we talk about effusion and diffusion, we bring up Graham, who did his work back in 1832. And what he saw is the rate of effusion, which happens to have the same symbol as root mean square speed, was inversely proportional to the square root of the molecular weight. So that is the relationship that he saw. Where would you be noticing this? Well, we would do it as a ratio. We would say, hey, this is gas number 1. That would be its rate of effusion. And we would say it's inversely proportional to the square root of the molecular weight. This is like P1V1 equals P2V2. We're just using different equations. It's the same kind of math. So again, if we were in the classroom, I would have a long tube, and in that tube I would be putting in ammonia and hydrochloride gas from each end. I'm going to draw it in a moment. But before I go there, this technique was used to purify uranium in order to make the atomic bomb. I think I have to throw that in there. So let's see what happens here. We have a long tube, and I'll draw it right here. And on one end, we are putting in some HCl gas. And on the other end, I am putting in some ammonia gas. And I'm going to let the two of them come together. What, why, and where am I going to be seeing anything? Well, the chemistry is when ammonia gas reacts with HCl gas, we are going to go form NH4Cl as a solid. So if we were in the classroom, you would be observing this, and I would ask you to predict where along the tube am I going to see a solid precipitate form. This is the setup for crunching the numbers, and I kind of drew around it. But here is where I'm looking at the rate of NH3. It's equal to the molecular weight of HCl divided by NH3 times the rate of HCl. When I put my numbers in, I get two different answers. One of them says ammonia is moving at 1.5 times the rate of HCl, or 0.68 times the rate of NH3 is equal to the rate of HCl. So if I were to say, where is my solid going to form? Well, the ammonia is moving faster. We would see in the classroom that this would be the white solid. Maybe I didn't draw it quite right. But the white solid, indicative of NH4Cl, it will be closer to the HCl input of the gas, all right? So what I'd like to make sure you do is the text example. If you're given the rates of effusion, find the molecule, and it's really, that's one example, and the other is 10.88.